second one is combustor instability, and the third is system instability. So we will first briefly look at what these individually mean, and then we will start looking at the details of each of these. But before that, we should also first of all look at the word instability regardless of combustion. Okay. The idea of instability is not specific to combustion. It's something that comes from what we call as perturbation theory. So essentially it's an idea, of course, much more than that. I think it's a much more commonsensical idea. There are lots of things around us which show inherent characteristics of instability. Some extremely social examples would be like, for example, if I don't do exercise, I grow way heavier, and then that makes it more difficult for me to do exercise, and then I keep growing heavier, and so that's an instability, right? Or the other example is if people stop using public transport, then public transport run in losses, therefore they run less buses, and therefore we still are going away from using public transport, the buses now stop running, and so on. So lots of such social situations, or human situations, you can go through what's called as instability. So the basic idea is, if you now have a system which we think is in equilibrium, and then we now try to make a lot of small perturbation, question is the system coming back to the original position, or is it goes away from the original position? So here there are a few different things that are kind of important. You could actually have a dynamic system which is in equilibrium locally, that means at a particular set of parameters. So for example, in a flow system you could have the parameters could be Reynolds number. In a combustion system the parameter could be equivalence ratio. So you could now be running an engine at a set of conditions like airflow rate and an equivalence ratio, pressure and initial temperature of reactants, and so on. And then for these set of conditions you now have some equilibrium, and what we are talking about is perturbing about an equilibrium for this given set of conditions. If you now move your set of conditions, you now reach a new equilibrium, and that need not necessarily be stable as the previous set of conditions for which you had an equilibrium. So equilibrium doesn't necessarily mean stability. You could have a unstable equilibrium or a stable equilibrium. So for example, the best example is, for example, for you now have like a rod that is hanging from a pivot, and then if it is like this, and then you now tap it, it's supposed to go through a sinusoidal, a oscillatory motion like a pendulum, and what's called as a set point, that is the equilibrium, is where it's actually hanging down because of gravity. But then if you now can also hold this rod up here, then that's also actually in equilibrium. The weight of the rod is actually being balanced by the support, but now you try to tap it, it now starts going farther and farther away from the equilibrium. So the top position is an equilibrium as well, but it's an unstable equilibrium when compared to the bottom position. So the examples that we talked about, where we are talking about the physical weight of a person versus the exercise, is a situation where we were talking about something that was unstable. So that's what is instability connoting there. That means you have a situation, and then any small perturbation keeps you going away from that position. So that's what we really mean by instability to begin with. Intrinsic instability then is actually a instability where you don't have anything else coupled to the combustion. It's only the combustion itself that is unstable, right? So the flame exhibits instability by itself. A combustor instability, on the other hand, is a system of flame coupling with acoustics in the combustor, so this is a flame acoustic system where you have a feedback loop between the flame and the acoustics in the combustor. We will talk in greater detail about this, but essentially here it's not a standalone combustion that is going unstable, it's combustion coupled with acoustics in the combustion chamber that is going unstable. So that is the combustor instability. The system instability is feedback with, let's say, fuel supply, air supply or oxidizer supply, etc. That means it now is a bit more specific to how the system actually is configured, which is going to cause this instability. Again, we will talk in greater detail about this. So let's first talk about the intrinsic instability here. We shall talk about Premix Flames, or I should say Premix Flames. I shouldn't say plain Premix Flames because that's the point of contention as far as the instability is concerned. Let's look at Premix Flames. We have talked about the issues involved in here. We could talk about two things. One is the thermal diffusive instability, and the other one is the Darius Lando instability. And we have actually discussed this previously when we were talking about corrections to the laminar flame speed. Okay, and there we were basically talking about these effects of the flame curvature and the flow divergence effects, right. So what we were basically saying is, if you now have a planar flame, and then let us suppose that you now perturb this, right, then we have the situation where the heat is actually going radially outward in a flame that is curved concave relative to the upstream reactants. Of course, the flow is going from left to right, and in this case the heat is actually converging. While the heat is diverging here and converging here, the reactant flow or the reactant diffusion into the flame is happening the opposite direction. That means here all the reactants are actually converging towards the flame, and all the reactants here are actually diverging. So you have a lesser concentration of reactants in this flame, but they get heated up more, but you have a greater concentration of reactants, but they are getting heated up less because the heat is getting distributed. So now the question comes, what is the effect of Lewis number? So the thermal diffusive instability is directly a consequence of non-unity Lewis number. So when you have a non-unity Lewis number, then the heat conduction upstream to the reactants and the reactant diffusion downstream to the flame, they don't happen exactly over the same length scale. So when you and we have gone through this, we said when we have a larger Lewis number, that means your conductive effects are actually more when compared to diffusive effects, whereas it's opposite. So depending upon this, what you will find is there are ranges of Lewis numbers for which you will have something that is unstable, right. So this leads to unstable flame or oscillatory or stable flame. Right. What is meant by that is, I mean, again going back to the idea of instability in general, if you now have a equilibrium point and then you now give it a perturbation, and then you are now trying to track what happens to the amplitude of the perturbation with time, right. If it comes down like this, that is stable. If it now grows like that, that is unstable. The amplitude keeps on exponentially growing, that is unstable. The other possibility is it looks like it is actually coming closer to the equilibrium point, but it begins to oscillate, right. For clarity, let's also look at a couple of other situations where it could look like it is coming back, but then it oscillates and then its amplitude keeps growing, right. So this is oscillatorily unstable. And the third situation, the other situation, of course, is when you now have something that comes back in an oscillatory manner, right. So then this becomes stable. That means the amplitudes are dying down, but in an oscillatory manner. So there are many such possibilities. What we are talking about here is a possibility where the amplitudes remain constant. In fact, this refers to like the way the pendulum behaves. So when you now give it a tap, it looks like it comes back, but it kind of misses the equilibrium point because of inertia, and then oops, it went to the other side. Then it goes back, and it looks like okay, it's going to be stable, but oops, it went to the other side, and so on. So since you now look at a displacement, and then at a small perturbation, it looks like it's coming back, you will tend to think that it is stable, but that is what is called as only static stability. But dynamically, it now actually attains a neutral equilibrium of an oscillatory state, okay. And then of course in nonlinear dynamics they would refer to it as a Hopf bifurcation and so on. We will not get into all that jargon here. We will just say that, for example, you could lead to an unstable flame. That means when you now have a plain premix flame that is perturbed, it could now get become increasingly non-planar, right. So if it now starts getting curved more and more, that's an unstable flame. A stable flame, on the other hand, is where you now have a perturbation and then it gets back to being planar, right. A oscillatory flame is it now starts actually oscillating with a certain constant amplitude, right. So there are many such. In fact, the oscillatory flame is something that I'll talk about more in the context of partially premix flames. But right now you could say that for different Lewis numbers you can find that you can say the flame becomes unstable or the flame. And typically the Lewis numbers, of course, the Lewis number is actually a function of the reactant, okay, so because it involves the diffusivity of the reactant. So usually we are talking about non-unity Lewis numbers of the deficient reactant, because the deficient reactant is the one that the flame is more sensitive to, okay. The other kind of instability that we are talking about is what's called the Darius Lando instability, or simply hydrodynamic instability. And this is also something that we talked about in the context of corrections to the laminar flame speed in some sort of a steady state framework, but not necessarily in a instability framework, where what we are talking about is a premix flame can be thought of as a line of discontinuity between two different regions of different density, right. So you have the cold reactants that are denser, you have the hot products that are lighter, right. So because of which you now have a flow, what we talked about at that time was because of which you now have a flow divergence or a flow convergence behind the flame, which could in turn accentuate the curvature. So the basic idea about the Darius Lando instability is if you now have any interface between two fluids of different densities, it is inherently unstable, intrinsically unstable, or unconditionally unstable, right. So that's the kind of mechanism that you will see prevailing in flames as well. So that is like similar examples are, for example, You can look at like a surface of water a surface of water with air being the other side. So you now have two fluids of different densities separated by the interface. Now this interface now is susceptible to perturbation, and when this perturbation happens it now starts forming waves, right. So similarly flames also are actually interfaces between fluids of two different densities, colder denser reactants and hotter lighter products. So you would face hydrodynamic instability as well. In practice you have a combination of both, and therefore it is not very unrealistic to expect plain premix flames in the laboratory. That is not because they are actually both thermal diffusively stable and Darius Lando stable. They could be unstable, but those instabilities are cancelling each other, alright. So where one of the instabilities is actually causing it to go away from the original position, the other one is trending to actually get it back to the original position, and so on. So one of them could be destabilizing, the other one could be stabilizing. The stabilizing force, the stabilizing mechanism could overwhelm the unstable mechanism, or even if both of them are trying to be unstable, they counteract in such a way that you now get a stable flame. So this is possible. Now in the extreme case where actually you have a unstable flame and you now have this curvature keep on growing, then you get into a regime called cellular flames. So this effectively leads to cellular flames, where the premix flame is no longer planar but actually breaks down into many different cells, and it now reaches a new equilibrium and a new stable equilibrium where it exists as these cells, and therefore that kind of a flame structure is what is called as a cellular flame. A cellular flame is also kind of structure also observed for diffusion flames. This is diffusion flame instability. So if you now begin to talk about diffusion flames under so you can also expect cellular flames under some conditions. In fact you could expect that the thermal diffusive instability is predominant in diffusion flames because you are expecting diffusion effects to be important there. Darius Lando instability is not as common because you don't really see like the density jump happening as much as in a premix flame. So premix flames are more susceptible to that, but in reality when you have a non-unity Lewis number and you have varying density with temperature, you can expect both mechanisms to prevail to different extents. Then finally we have the situation of partially premix flames. And here there are some regimes of Lewis number greater than 1 where you get oscillatory flame. That means you're looking at something like a triple flame or something that's more compact, essentially like an edge flame. So if you now look at a triple flame like this with a splitter plate, and then you have fuel on this side, oxidizer on that side, you have a trailing diffusion flame, and you have the fuel rich branch and the fuel lean branch. There are some Lewis numbers for which this entire structure actually begins to oscillate back and forth at a constant amplitude. Okay, and of course if you now change your Lewis number or change your Damkohler number, in fact the Damkohler number dictates how much should be the standoff distance. If you have Damkohler number is effectively a indicator of the finiteness of the chemical reaction rates, and so the more finite the chemical reaction rates are, or less close to infinite chemistry, the Damkohler number is more finite, and correspondingly the standoff distances increase. And of course even under stable conditions you will not get equilibrium flame established less than a certain Damkohler number, and the flame blows off. That is a steady state. There is a steady state solution doesn't exist. Okay. Now for a steady state solution that exists, this is susceptible to small perturbations for some Lewis numbers greater than 1 where it actually undergoes oscillatory instability also. Okay, so that is the case where we were talking about a constant amplitude, and of course the amplitude and the frequency are functions of Lewis number and Damkohler number, and they change continuously. So that is something that and of course you can also think about the fuel oxidizer ratio, concentration gradients that the flame is subjected to, and so on. So these are the parameters over which the oscillatory instability will manifest. So that's about intrinsic flame instabilities. Now let's look at combustor instabilities. Here basically what's happening is, if you now have a flame that is being perturbed, the basic thing that we are looking at is what's happening to its properties, and these properties mainly in this context could be the heat release rate, the temperature downstream of the flame, the density downstream of the flame. Of course all these things are related. Okay, so the temperature rise is related to how much is the heat release, and the density fall is related to the temperature rise, right. So if you now perturb the flame and the flame moves around, then the heat release rate undergoes a fluctuation, and therefore the temperature undergoes a fluctuation, and the density undergoes a fluctuation. So when you now have these fluctuations, they set out acoustic waves away from the flame, and these acoustic waves will now go and get reflected at the ends of the combustor, and then get reflected back and set up a standing wave, and the standing wave is now going to actually fluctuate this flame further, and when the flame fluctuates further, then it sets out a stronger acoustic wave, and so that the prevailing acoustics now begins to get amplified, and this amplified acoustic wave sets up a stronger standing wave which now oscillates the flame even further, and so on. So now you begin to understand that the amplitude of the acoustic oscillations will keep on rising. In fact the amplitudes of every oscillation that is there keeps on rising, right. So this is essentially the coupling of the flame with the acoustics. Of course before I proceed further, what I should say is, this is the situation that I just described is something that is very simple to think about for a gas phase combustion, alright. That means you now have like a gaseous reactant, that is gaseous fuel mixing with gaseous oxidizer, maybe a premix flame, maybe a diffusion flame, right. But essentially some gas phase flame that is undergoing this and then causing this situation. But before we proceed, I also should point out that there are two ways of thinking about this depending upon what we are dealing with. On the one hand, you could now deal with gas phase systems, gas turbine combustors, gas turbines combustors could be gas phase systems or liquid phase systems. There are land based gas turbines which use like natural gas for powering them, or there are things like aviation gas turbines which use liquid fuels for powering them, so you could have the liquid fuel as well in these, and then you can also talk about liquid rocket engines, liquid rocket combustors, and so on. But on the other hand, you now also have solid rocket combustors, and the way things happen in a solid rocket are slightly different from the way it happens in these. Okay. So we will first discuss what happens over here, and then we will go back and look at what happens here. So let's look at the gas phase combustion, for example. Gas phase combustors could have, of course, many times we are interested in gas phase combustors being having premix flames. So you could think about a combustor in which let us say a typical geometry for us could be what's a very simple geometry. A simple geometry for us as far as premix flames is concerned. Let us suppose that we now take a V gutter. Okay, so if you now take a V gutter, we would like to think that you can have a flame that is established like that. So it is anchored at the edge of the bluff body, and then it actually extends out. We talked about this when we were dealing with flame shapes. What we said was the flame is trying to travel with a propagate with a turbulent velocity, and then so it actually orients itself in such a way that the local normal velocity component matches the turbulent flame speed, and so on. But then the question is, what happens when the flow velocity begins to oscillate, right? So when the flow velocity begins to oscillate on top of a mean flow, right? So you have a mean flow, but it's now going to go back and forth. So why does the flow velocity oscillate? To start your thinking on the loop, let us suppose that there is a perturbation, and then what we want to point out that this is going to actually give rise to more flow fluctuation. Okay, so what we are saying is when you now have a flow velocity fluctuation, you have a faster flow sometime and then a slower flow sometime. So when you have a faster flow, the flame is going to actually get more inclined, and when you have a slower flow, the flame tries to propagate still further in, and so it's going to go like that. So essentially now we think that the flame is going to flap back and forth like this, right? So when the flame tries to flap back and forth like this, look at what is happening to the flame area. So the flame area keeps fluctuating, and since the flame area is along which the heat release is happening, the total heat release in this region is now going to fluctuate, because you had a larger area over which the heat was released versus a smaller area over which the heat was released, and therefore you're now going to get heat release fluctuations because of the velocity fluctuations. And the heat release fluctuations now try to send out acoustic waves that amplify this oscillation, and when the oscillation gets amplified further, this oscillation is going to become wilder, right? So that's the instability that we were talking about. But unfortunately, life is not as simple as this. So what happens in reality is, when you're now trying to actually send this fluctuation, the flame simply doesn't move back and forth like this. Instead, it actually moves more like that. There is a perturbation that happens in bulk for the flow, which the flame tries to match, but there is also the perturbation that is being sent along the flame. So there are two ways in which this perturbation is propagating, one from the boundary along the flame and one in the flow field itself. So depending upon how long the flame is locally, the wave that is propagating along the flame starting from the boundary, and the flow fluctuation that is happening anywhere at any part locally on the flame, they are going to interfere constructively or destructively, and depending upon that, you are now going to get a wavy pattern. This now adds further to the flame area fluctuations, and on top of it we have to consider, now that you have a non-planar flame, then we will have to consider the flame curvature effects and the flow divergence effects on the flame propagation speed. Okay, so there are all these other things, and in reality the other problem that happens is the flame anchor point, where it is actually being held at the flame holder, that itself fluctuates, because at the anchor point we went through this dynamics. You now have a entrainment of non-reacting gases on the one hand and a heat loss to this, and this heat loss begins to fluctuate, the entrainment begins to fluctuate. So where exactly the flame stops away from the burner, that fluctuates, and that is where the perturbation is being sent along the flame. So if the flame itself were to move away and then you now send a fluctuation along the flame to constructively or destructively interfere with the bulk flow fluctuation, then the flame shape gets altered correspondingly, right. So these things actually complicate this matter. This is purely what we call as a kinematic effect. The moment we are talking about the flame speed and a flame sheet and the flame is trying to balance the flow, that kind of idea, all the dynamics is considered within the flame. We have long gone past the point where we have to worry about the dynamics of the energy balance and the species balance and so on that happens within the structure of the flame. We only worry about how the shape changes now. So this is not even dynamics, it is purely kinematical effects, right. So these are some of the things that happen in the case of let us say premix flames. Similar things also happen in diffusion flames, except that we do not really talk too much about it. So let us suppose that you now had a simplified gas turbine construct where you now try to have a flame that goes like this, and then you now adopt a Burke-Schumann approach to strictly get a diffusion flame, because if you did not adopt a Burke-Schumann approach where you had a flame sheet assumption where the flame sheet is coincident with the stoichiometric surface and so on, all the ideas that we had, then we will have a flame standoff. You will have partially premix flame, you will have flames that look like more like this. That's what happens in reality, but for the sake of thinking about diffusion flames, let us think about like a Burke-Schumann flame, and suppose that you now have a overventilated Burke-Schumann flame, and now let us suppose that we now oscillate the flow on top of a mean flow. The mean flow was the one that gave rise to this flame shape, all right, but the moment you now oscillate this flow, you now begin to actually have, well, what would you expect? The first order effect, of course, is the first order effect, as we saw earlier, is if you now temporarily have a flow that is going faster, then it should actually prolong the flame, right, and for the other half of the cycle where the flow goes slower, it should now shorten the flame. So the flame shape should now begin to change like this, and therefore the flame area fluctuates again, and the heat release is happening along the flame sheet. Very similar ideas to what we had just talked about for the premix flame exists. So we could think like that, but that is a more simplistic idea. What in reality happens is like what we talked about. That means you also have like a wavy structure that goes on for this flame, depending upon the frequency and the length scale of this flame, and therefore you have to factor that into account. And so typically what we are interested in is what is the heat release fluctuation as a ratio of the mean heat release for a given velocity fluctuation as a ratio of the mean velocity. So you have now two things. One is heat release fluctuation over the mean heat release divided by the velocity fluctuation over the mean velocity, right. So this is a quantity that is typically referred to as the flame transfer function or something like that, and there is a lot of work that's been going on in these things. Essentially we are looking at what is the flame response to the oscillations, and what we can understand in the gas phase flame context is these oscillations are essentially happening because of the velocity fluctuations. So you don't expect a big effect for pressure fluctuations that are associated with acoustic waves. It's the velocity fluctuations that are causing the havoc, right. So a quick fix for you would be, if you find that there are huge oscillations that are happening, is it possible for me to locate where the flame exists, the bluff body here or the flame the fuel injection point here, in a place where I have what's called as a velocity node in the standing wave mode. So you have a standing wave, and you have velocity nodes, then try to locate the flames there so that the flames are more silent, right. So they are not really subjected to huge velocity fluctuations no matter what the amplitude is, because regardless of what the amplitude of the perturbation is, the node is going to always have a 0 velocity amplitude, right. So if you now try to locate your flames closer to the nodes, of course the point is the presence of the flame itself changes the mode, the acoustic mode shape. Okay, so you have to actually sort of dynamically chase the velocity node and then locate it. So it's a little bit more involved than just saying that. And similarly, there are other problems, like many times, in fact one of the things that I have not talked about here is, if you now have a bluff body, you now have a vortex shedding that's associated with it, and the vortex now begins to curl the flame, and that increases or decreases the flame area, and these vortices are shed. So when the vortices are shed, they take away a part of the flame and burn them somewhere there, and then a new flame is established and so on. So you now have heat release oscillations that are associated with vortex shedding, and now you have a new time scale in the problem related to the vortex shedding frequency, and how is this vortex shedding frequency going to relate with the natural acoustic mode of the duct that is satisfying the acoustic boundary conditions, will now also begin to play a huge role in trying to dictate what the acoustic amplitudes are, and the amplitudes of the other fluctuations. So this is now getting to be quite complicated. In the solid rockets, on the other hand, you have a very different situation. What you have is, now if you think about a solid rocket, obviously we are talking about combustion chambers, so combustor instabilities. So we have to look at a solid rocket motor, in which if you now have a propellant that is shaped like this, then everything that's happening that matters to us is within a very short distance from the burning surface of the propellant, and within this very short distance, effectively, if you now for example think about this region, and then of course we talked about a homogeneous propellant which has like a premix flame, or a heterogeneous propellant where you have, let's say, something like oxidizer particles, and then you've had some diffusion flame, maybe some edge flame here, and then a monopropellant flame there, and so on. The question is, what is the effect of the acoustic oscillations in this chamber on this flame? And here typically the way the solid propellant rocket design is done is to look for how is the burning rate of the propellant dependent on pressure. Okay, so and usually you get a picture that looks like the R goes as P, like that, and this is actually a log plot. Okay, and what we are talking about now is, if I increase my pressure, then I expect that the reaction rates should increase, therefore the flames will now get attached closer to the surface, and therefore they will send in more heat to the burning surface and then give rise to more gases that are coming out, right. So as the pressure locally increases, we expect that the rate at which gases are coming out should increase, or the burning rate should increase, the instantaneous burning rate should increase, and therefore it now puts in more gas into the chamber, and that pressurizes the system more. And if the pressure, and when you now have a less pressure because of the acoustic perturbation, then the burning kind of slows down and it puts less gas into the chamber, so that relieves this, and then the pressure decrease further decreases. So when you now have an oscillatory pressure, then the way the propellant burns could, or most of the time does, actually help the pressure to increase and decrease more and more. So here, instead of looking at a velocity fluctuation based flame response as we did in the gas phase combustor, we look at a pressure based propellant combustion response. Alright, and here again we can now think about a response function where this is actually not in terms of heat release fluctuations and velocity fluctuations, this is in terms of mass fluctuations relative to pressure fluctuations. So this, the characteristic that we are using here to look at how the propellant responds to the acoustics is slightly different from how we deal with in this class of problems. Finally, let's now look at the system instability. This again is not directly related to combustion, but it affects combustion. So this is mainly seen in gas turbines and liquid rockets, particularly gas-based gas turbines. Liquid rocket, you can say fuel here, you can say propellant here, both of them together you are looking at the feed system. So the best or the simplest example that we can think of is when you now have a situation, actually it doesn't have to be fuel, it could, okay, fine. So let us suppose that we have air coming in or oxidizer coming in, and then you now inject your fuel on the side, and so that means in this region the fuel and air actually mix with each other, and then you now have a premix flame that is set up there, right. What we are now saying is, well, now if we have a perturbation, okay, this flame now perturbs and then gives rise to heat release fluctuations, which now sets up acoustic wave. So you now have a acoustic standing wave from here to there, of course taking into account like a step change that is possible, right. So in this acoustic mode where the fuel inlet is actually located, the pressure here is actually going to fluctuate because of the acoustics, and when the pressure fluctuates you now have a delta P fluctuation for the fuel inlet, and that's going to correspond to actually a fuel mass flow rate fluctuation. So when your fuel mass flow rate fluctuates for a given constant mass flow rate of air, then you have what's called as equivalence ratio fluctuations. So this leads to something called phi prime. We are not even talking about the effect of u prime or the velocity fluctuations, we are talking about the effect of the equivalence ratio fluctuations. So what basically happens, you now have for one half of the cycle where the pressure is actually increasing here, then you have less fuel coming in, so this is slightly leaner than design point, okay. So when it is leaner, the flame now burns slower, therefore it elongates. But then when you go to the next half of the cycle where the pressure decreases, you have more fuel that is coming in and then mixes with the air. But the crucial thing is, it is not an instantaneous mixing everywhere in the flow field in this inlet. So you now have a fuel pocket that now convects down at the flow speed. So the question is, when the flame is trying to come back, if you now have a fuel pocket that arrives there with, of course, mixed with air and makes it less leaner, then the flame will want to come back more. That accentuates the instability. So when we say when the fuel pocket comes here, that means it's got to do with what is this distance relative to what is the velocity, right. So there is a convective time delay for pockets of fuel to mix with air and come. So the equivalence ratio now fluctuates because of the convective time delay, and that can feed back into how the flame wants to flap back and forth and change its area and get along with the combustion instability because of that. Similarly, in the case of liquid rockets, typically what they do as far as design is concerned is, in order to avoid something like this, they have an injector plate which is designed to take a delta P across the injector plate. The pressure, the injection pressure is essentially the pressure upstream of the injector plate relative to the combustion chamber pressure. So it's essentially a pressure differential, delta P, and the way they design this is they want to have this delta P to be at least about 20% of the chamber pressure. That means the injection pressure upstream of the injector plate should be 20% more than the combustion chamber pressure, so much delta P, so that any oscillations that are happening in the combustor is not really felt upstream. You now have a fairly robust high pressure over here which can push the propellants pretty much at the same rate regardless of the small fluctuations there. If this were only marginally more, for example, right, then any fluctuations here will propagate upstream significantly and cause fluctuations in the flow rates of the liquid fuel and liquid oxidizer, and therefore now when they mix and burn, everything is going to oscillate, and then that could actually increase these oscillations even more and more. And in fact many times when this is not done right, then these fluctuations can actually propagate all the way upstream to the tank. That's where they get arrested. So now your feed line has a certain acoustic characteristics. Anything that is confined has acoustic characteristics because of possible reflections and standing wave modes and so on, right. So the feed line can amplify the acoustics if it resonates with the oscillations that are there in the combustor. So many times like the combustor could have something called radial modes, whereas the feed line could have a longitudinal mode at the same frequency and so on. When these things couple with each other, then these oscillations become significant, and then the whole system begins to have oscillations all over the place, basically then telling us that system instability is a very big problem, right. But of course those are now getting into mechanical details, a little bit moving away from combustion, but you have to keep in mind that the heat release fluctuations in the combustion is like the primary driver for any perturbations to grow, and all other things begin to couple with it. So as a matter of fact, similarly when you now look at things like solid rockets where you have let us say what's called a segmented rockets which have inhibitors, the inhibitors can now protrude into the flow when the propellant burns, and it can now produce vortices, and these vortices give rise to pressure oscillations, but that is not significant many times when compared to what it can do to the propellant combustion response to become significant. So this is like a trigger, and then the propellant combustion response now takes over and causes the combustion instability. So many times there are a lot of other things in the system that will go together with the combustion event once the combustion event is inherently unstable or susceptible to acoustic instability. So the system instability typically is a secondary effect. It's a combustion instability that we should mainly focus on trying to damp as much as we can. So we don't want to get into how to damp these things, just wanted to point out that just wanted to point out two things. One, such problems exist. Things are not as steady as what we have been going through. They are inherently unsteady, or they are susceptible to perturbations. That is number one. Second, we can understand many of these things based on whatever we have studied with laminar flows, laminar combustion, and steady state ideas and so on. But the problems are a lot deeper when compared to what meets the eye in this lecture. Thanks a lot.